Hi, I'm Philipp. I work at Sonar, and in this talk I present to you the notorious BUG, the most popular bugs in code smells and C in C and C++. Well, at Sonar we build program analyzers, and occasionally we do analyze some code, and I will show you some findings of what we found. All right, can I have the slides, please? Yes, here we go. Ooh. Okay, so first question. First, what do we wish to find, actually? Well, I said to you we build program analyzers. So what do we find? At Sonar, we have something which is called rules. So we have different sets of rules for different languages. And as it turns out, we also have like rules for the C and the C++ languages. And rules are basically describing what not to do in a language, because it could like rip your leg off if you don't use it carefully. So those are basically rules for what not to do in a language, for what to watch out for, right? So, and we also have rules for C++, as you can see, right? You can also browse them. You will find those rules on the internet if you just Google for the right words. For instance, one rule is memset should not be used to delete sensitive data, because the optimizer might optimize it away because it thinks it is not really needed. So any sane cryptographic library has a safe version to memset something to 0 if you no longer need to use that memory block. Okay, so now we have rules, what not to do, and how do we find bugs? Well, we employ various techniques at Sonar. So let me give you a brief overview on the C family analyzer. So it's based on LLVM Clang, and the analyzer and the rules themselves are written in C++. And again, we use several techniques for finding issues, so violations of the rules that we came up with. Our workhorses are AST-based rules, AST matchers we use to check and verify if that rule holds really, or if we find violations. And yet another technique that proves to be quite fruitful is symbolic execution. I briefly want to talk you through that, such that you have an idea of how it's going on, how we find stuff, and then I show you what we actually found. So let me talk about AST matchers. Compiler Explorer is a nice website. You should all know about Compiler Explorer. And you can try out AST matchers yourself, basically. So what you can do is you can write a small C or C++ program, right? Attach some compiler to it, and then say, hey, please dump the abstract syntax tree for that program. And what you're basically looking here, that colorful rainbowish-like piece of code or textual representation, is the AST, and in fact it's Clang's AST as it is used in the compiler. And you can see, hey, we have a small add function taking two integer parameters, right? Summing them up together and then returning an integer parameter. And you find the same stuff on the AST. Who would have thought, right? So here you have the add function. It takes two ints as parameters, returns an int. You have some param-ra decals for A and B. You have the compound statement in curly braces, the return statement, right, which has the binary operator plus. And then you have some decal ref expressions to A and B, the function's parameters. And so what you can also do is, if you have that set up in Compiler Explorer, you can also use the Clang query tool. And this is truly great, because what people implemented as part of the Clang compiler is they implemented a domain-specific language, an embedded domain-specific language even. So technically it's still C++, although it looks quite outlandish if you compare it to your day-to-day C++, which you can use to describe queries which are then conducted on the AST. And here's such an example query, right? You ask for, hey, let's match, it almost reads like the English written language, hey, match a return statement which has as a descendant a binary operator, and then bind some additional tag to it, which here it's just a string OP for operator. And then it runs the query on the AST, and it will tell you what it matched, right? So the root binds here, it tells you, right? It's the whole return expression That is our root that we wanted to find. And it will also find for you the binary operator, and it also gives you that under the tag op that you assigned or associate with that. And so you now have the findings. You found the AST nodes you have been looking for, and then you can process that, right? You can even fix stuff and do some automated rewrites. You can report the findings, the AST nodes here you're interested in. And well, what can you do? You can look for AST patterns that are likely issues, right? That violate a rule in terms of code. So that's one great thing, and it works blazingly fast, and you can really find anti-patterns or patterns you don't actually wish to find in a fully automated manner just by having such a small description in that EDSL. So yet another technique is symbolic execution that we use in our day-to-day business. How does it work? Symbolic execution simulates the program's execution. And we use that over AST-based rules whenever we need control flow and some additional state to reason about a program and its properties. And what it does, it analyzes a program path by path, as opposed, if you're familiar with the data flow analysis, where whenever you have like branching going on and control flow merges at a common successor statement, you would need to merge the pieces of information before you then continue propagation. On the other hand, symbolic execution really does one path at a time. And unknown values are just symbols. And you may ask, okay, how is it useful, right? I mean, if you don't have values, just symbols. Well, we use branches and post conditions to constrain values and still like reason about the program to really get interesting findings. And I have an example here on the next few slides. So we have another simple function, like it's called entry, takes an integer, does some processing, and then ideally also returns an integer. So if you ask Clang for, hey, generate the control flow graph for that function, it will look like that. So, and symbolic execution now needs to analyze those for individual branches. So luckily, because of the two early returns that we hear, we can reduce the number of program paths. But in the worst case, right, for each branch that you have in your program, you have 2 to the power of n possible program paths. So you have quite a few paths in your program, who would have thought, right? But because of those two early returns, we only have like 4 paths that we need to analyze. And well, let's play analyzer now, and let's see what we can find. Maybe we can find something interesting. At the beginning of the function, we don't know anything, right? And let's see what we know. So we have a argument, integer argument x. I mean, that function is not called, right? We analyze it statically. So, okay, let's just do our best. And at the beginning, we know, okay, x can have any value between int min and int max, whatever that might be on your architecture or platform that you're building your software for. And then let's just analyze the program path that goes into that if, like that assumes that this if is true. Then you know, okay, if I can reach that point, I know for a fact that x must be between somewhere between 1 and int max. If I don't take that branch, I know at that point in the program, well, my integer x is somewhere between int min and 0, right? Somewhere in that interval. If I go here and enter that next if branch, well, flip coin doesn't give me very much, right? So just keep information as is. And if I enter yet the third if branch, I know at this point in the program, x is somewhere between int min and -1. Okay, and then I return, and okay, nothing really interesting going on. Hey, what if I don't take that second early return? I know for a fact that on this path, x is 0, exactly 0. Well, and that kind of ruins this operation here. I have a really bad time if I try to execute that. So, and that is symbolic execution, analyzing really path by path, opposed to data flow analysis, which would merge at each, whenever 2 branches go together and meet in a common subsequent statement. So in traditional data flow analysis, I would need to combine that piece of information at this point with that other piece of information, and depending on how you set up your analyses, in data flow analysis, you would just find that, okay, x is somewhere between min and 0. Well, that's still half of the integer range, right? So it doesn't give me very much. Okay, let's better not make a claim here. So those two pieces of information would need to be merged some way or the other. Well, and we keep it in separate in symbolic execution. So we would have that one path where we have this piece of information, we don't take that branch, and again, we end at this last return statement here with that information. That would be one outcome. And we also separately, again, analyze the path where we take, where we don't take this branch, we take the second if branch, and we don't take the third if branch. Then we end up in this situation where x is exactly 0, and we do have a serious problem because that is undefined behavior. And if you ask the Clang compiler, we can just give it some flags, because Clang also has a symbolic execution engine implemented that you can ask for stuff, and it will show you, hey, you do have a problem for that given piece of code. And so you can think of symbolic execution as a kind of bug prover. So whenever there's a path where something goes horribly wrong, it will throw an error at you and say to you, hey, check out this path because something serious is happening on that path. So too good to be true. That looks, a bug prover, isn't that great? But there is a catch. So again, analyzing path by path, if you have n branches, you have 2 to the power of n possible paths in the worst case. In our example, we had some early returns, so it reduces slightly. But geez, that is quite expensive, right? If you want to apply it to a whole program setting, can't be done. There's also Rice's theorem, which says, in 53, there was that famous paper, you can look it up on the internet, and this theorem essentially says, hey, all non-trivial semantic properties of programs are undecidable. And what is a non-trivial semantic property? That is one that neither holds for no programs nor for all programs. So quite a few properties are really non-trivial, right? Non-trivial semantic properties. What does it mean in practice? We constantly have to implement analysis algorithms which try to do their best, right? We cannot always be correct, and we just need to balance our findings. Do we want to have perfect precision? What does it mean? That means we don't overlook bugs, but at the cost of reporting false positives. So at the cost of reporting bugs that in reality are not really bugs. We just have to be, we want to achieve perfect precision, and therefore, if we are not sure, we say, hey, it's a bug, right? But if developers are confronted, if they enter the office 8 o'clock in the morning and they are confronted with 100,000 bugs that the analyzer found, they have a really bad day, and they probably just close the laptop and no longer use that tool. Right, so that is not going to happen. On the other hand, perfect recall, what would that mean? That would mean if we are not sure, we better not report, right? Because we don't want to annoy users. But then we have too many false positives. What I just explained it the other way around. Yes. Sorry, I did. But you are smart. You just thought it through. So we don't want to have issues missing, important issues missing, and we also don't want to be too noisy. So it's always some kind of trade-off, right, that we need to fulfill. Still, it's tremendously useful because, as you can imagine, an automated tool can go through each of the program's path much faster than a human reviewer, right? So I still give the technique that. You can also check it out on Compile Explorer these days and see what symbolic execution really can do. So you can write some really rubbish code, as I did here. I tried my best to come up with insane stuff you should never write. You can assign a compiler to it, attach a compiler to it, and then to the compiler you can attach yet an additional tool, and you can, for instance, attach Sonar, and then it will give you all the findings using AST matchers and also symbolic execution, and then you can go through your issues and fix them. So if you're interested in that and seeing what the technique can really do, or those techniques can really do, just feel free to check it out on Compile Explorer. So now I told you what we wish to find, like techniques that we use for finding like offending cases, and let's derive a top 10 list. So what's our data source? So at Sonar, for each bug, code smell, or vulnerability, we have a corresponding rule, which also has an ID. And what I did is I pulled the statistics from our software as a service cloud solution. And okay, now we have like a whole bunch of data, and the question is, what should we use for ranking, right, to create the top 10 list? Should we just rate and rank by number of issues caused by each and every individual rule? Or should we take the issue percentage? So like for a given rule, what is the percentage of issues that it causes or that we can find, like offending pieces of code, that's the byte? Or should we basically use the project percentage, how many projects that we analyzed are affected, that what we call the reach? And I thought it would be a good idea, maybe let's use the outreach per rule, which is byte plus reach divided by 2, so just average. Because if you have a gazillion of issues and only one single project is affected, then maybe that project has some inherent flaw, or I don't know, maybe it doesn't seem really important. But if an issue or a rule causes transitively a huge byte and has a huge reach, then it is probably really important and we should do something about it. So what did we find using that kind of ranking? Well, when I compiled the slides and I like looked at the numbers and I ranked them, I had a tough time. So that was really bad. Looking at the type of issues, it almost seems ridiculous, at least to me. So let's give it a shot. Let's look at it. Uninitialized variables. Great. Buffer overflows, null pointer dereferences, unreachable code, memory and resource leaks, identical expressions on both sides of a binary operator, which seems fishy at least. Function return values missing, identical branches, destructors should not throw, so destructors that throw exceptions, which leaves the destructor, and single iteration loops. So I mean, what did we expect, right? But I mean, it's 2024, right? And still we are bothering with those issues, and that is the earliest rage quit I could find on the internet. But after having created this slide, I was like done for the day, really. So it seems bad. With modern C++, well, most of those things should no longer happen, right? And the other things is just unconcentrated developers who coded like for the entire day and then concentration level already hit rock bottom and okay, let's call it a day, right? So I give you the later one, right? But uninitialized variables, buffer overflows, that is really not good, let's say. So let me briefly talk you through them, and then I also show you some real-world examples. And I hopefully can convince you that those problems are real. And those are the reasons why C and C++ are criticized for all the time. And in reality, yeah, it's kind of for a reason. So what can we do? Uninitialized variables. Well, do initialize your variables, right? Maybe let's start with that. Turn on compiler warnings. And also use maybe W error. So like also warnings are hard errors and you cannot compile. The compiler refuses to compile a program for which it identifies warnings. So maybe that's a good thing as a starter. Unfortunately, however, it's not so easy. Okay, can't blame the compiler, but if you have this piece of code and you enable both of these flags, the compiler is perfectly happy. It's good code for the compiler. What happens? We have an uninitialized local variable a, integer, uninitialized. We put it to magic init. I always love this function here. It takes a ref to an int and doesn't do anything, and then it returns that variable a, and the compiler says, okay, hey, all good. Why is that? Because in order to reason about the program, you need pointer information, points to information, and the compiler says, hey, ooh, that can get arbitrarily complicated. So if I'm not sure, I better not say anything. So the compiler would be completely happy with that piece of code. Any sane analyzer would immediately throw a warning or an error at you and say, hey, go fix that and do initialize that variable, right, for a good reason. So yeah, what to do instead? Well, if you don't know better, maybe use default initialization, right? You could just add curly braces here, and at least you have 0 written to that piece of memory, even though that might be logically an error at a later point because something else would not expect 0 in that memory cell, but that would be deterministic, right, at least. So you would have a deterministic bug instead of some undefined behavior crap that you don't want to have in your program. So careful with default constructors. If you have like simple classes, even like pot types, plain old data, like say you have a point type with two integer members x and y, and you just spell out a default initializer, and you don't, in the default initializer, if you don't default initialize the members, they just stay uninitialized, right? So also, especially beginners fall into that trap, I feel. So yeah. What else? If you, and this situation happens quite frequently in practice, so if you have to do some like more advanced computation to figure out a good initial value, if you need to check some conditions or whatnot, well, then just use an immediately invoked lambda and check some condition, return one value. If that condition is true, return another value if the condition is false. Immediately invoke it, and then that thing will be initialized. Can also be done if you have multiple coupled variables, so you can just have return stud make tuple, and then just use this modern C++ expression, not so modern anymore at this point, but where you can decompose it and then have your variables x and y using immediately invoked lambdas. Okay. Well, when in doubt, also feel free to throw dynamic analysis at it. Clang and GCC implement that already. Probably many other compilers do as well. You can use the memory sanitizer, whose job is to find uninitialized variables or uses of uninitialized variables at least. And then you can compile it with sanitizers. You can run your program and it will crash and give you a backtrace where you try to access uninitialized memory. Well, next point, buffer overflows. Well, first of all, you need to forget everything you know about C-style arrays. That is probably the best advice I can give you. And still, in C++ classes at universities, I mean, it's still what is still taught when you like visit a C++ course and take a C++ course. It's like C++ 98. So yeah, it's C with classes, and we have new and delete instead malloc and free. That is not really the way it should be used. So instead, if you need a fixed size array on the stack, use std array. Rather than trying to do your own string manipulation, string buffer management, and you can only, I mean, you never succeed, right? It will always be wrong. So you use std string. If you have something that should live on the heap because you have like a gazillion of elements you need to maintain somewhere, well, use std vector to keep them on the heap. And these days you can also have like in-place vector, which as far as I've been told is like some vector with some initial stack capacity, and if that ever is like too small, then it will reallocate on the heap, and you can use that instead. Prefer range-based for loops, and you can use that with those containers. And also, if you use those STL types, well, you can benefit from all the functionalities that are provided with algorithms, right? And I also feel in general C++ evolves for the better. Well, if you need an index, just you can use std views enumerate, and let's say v is a vector of integers. You can use such an expression to have the integer value in that vector for each iteration, and also an index starting from 0, right? Which kind of in many places is more sane than having like an additional loop counter, and then you hopefully increment it, right? And maybe you have some exceptional cases where you have some condition in your for loop to maybe not increment it, or maybe you do it twice, or maybe once less, depending on the condition. So that only sets you up for failure. And we also have yet additional handy functions like std erase and std erase if that you can use for vector, for instance. I still remember the times when you had to, in order to get rid of elements in a vector, where you had to use the remove erase idiom, and it is hugely complicated to explain that to students. It's also kind of insane to use that kind of crap. So why not just use std erase? You give it a vector and you give it an element that should be removed, or you give it a lambda function that serves as a predicate in erase if, and then just it erases what you want to erase. Why not like use it as simple as that? Well, you say, I have an old code base, I cannot really touch it, and I can't use like all that new shiny modern C++ stuff. What else can you do? Well, I have written some points, and there's material link behind that, so in case you're interested later on, you can check. For all code bases that you cannot really touch, well, use sanitizers, use fortify source of GCC, maybe use decannaries, use address space layout randomization, and maybe also use fuzzing in order to like find bugs, right, and fix it to make your stuff more stable, your old legacy stuff more stable. So throw everything at it that you have that you can make good use of. Well, null pointer dereference, it's famous. It's like Tony Hoare's $1 billion mistake. He mentioned that in one of his talks. Who's that guy? It's a famous computer scientist. He won the Fields Medal. And he introduced null references in Algol in the development of that language. And there's this famous quote. Yeah, it's quite long. I still read it out because it's great. I also linked the talk, so really interesting stuff. So that's a direct quote from him. I call it my $1 billion mistake. It was the invention of the null reference in 65. At the time, I was designing first comprehensive type system for reference in an object-oriented language, Algol W. My goal was to ensure that all use of reference should be absolutely safe, with checking performed automatically by the compiler. But I couldn't resist the temptation to put in a null reference, simply because it was so easy to implement. This led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. So, well, the intention at least was good, right? But it was still messed up, kind of. Well, ensure your pointer is not null, right? Before you dereference it. And I feel there's a slight misconception with pointers. Like, yeah, okay, for pointers, I don't need to check if anything is there, if somebody is at home. There's nothing special of null if you think about it. If you have a std optional and you wrap some value in that std optional, you would never come up with the idea, okay, I'm just blindly using it, right? You would always check if that optional has something in it and otherwise act accordingly. Well, why not also do it for null pointers, right? And well, in C++, we not only have pointers, but also we have references. And if you really want to kind of say, or if you want to have as a precondition that a graph or anything for that matter really is not null, cannot be null, then, well, pass it as a const reference or just as a reference rather than a pointer, which might be null. Well, technically you can still misuse that and you can write some crappy code where you have a reference which then eventually goes to null, but that's really not how the language should be used at all, right? So maybe use reference. Unreachable code, what do we have here? Indicates logic flaws, source of confusion, original intention is unclear, untested, unmaintained code. Hopefully then that stays dead and unreachable, because otherwise, you're into trouble. I don't need to explain to you Apple's infamous go to fail bug, right? Where we had some unreachable code, and that is problematic. So don't write code like that, maybe. If you need a feature flag, really, because we see people writing that code, and then this is basically under feature flag, just literal 0, and then, okay, it's hard to read that this should really be a feature flag. It's really dubious, let's say. So if you need a feature flag, then we say, okay, hey, that is one of the very few exceptional cases in which global variables are okay-ish, right? Where you have a const expression bool, for instance, enable feature X, and then you can flip that switch, and that is the same way which we recommend, because most of the time a feature it spans more than one function. And if you have at various places like if null or if true, that is really, it sets you up for misery. But we actually see that in practice, so please don't do it. Well, what else? Resource leaks. Manual memory deallocation is a code smell. And if we analyze your code, we really report that. So any appearance of new or delete, we throw an issue at you and say, hey, you shouldn't use new and delete. And for only those very few exceptional cases, you can say, okay, hey, this is a false positive. In this case, I really need it. I know what I'm doing. Famous last words. But yeah, by default, this is really an issue, and we, in our analyzers, we throw issues at you for doing that. So what you should do instead is use RAII, that famous acronym here. So resource allocation, no, what was it? Resource acquisition is initialization. So thanks very much. So you acquire resources on construction and free resources on destruction, or whatever it is needs to be done, like closing a database handle at the end of the destructor. So use that. If the object is too large for the stack, well, allocate it on the heap, have a unique pointer, and job done. Multiple users, if you want to use it the Java way, just use make shared, and then you have Java, kind of. No, use shared pointers, right? And then it's still cleaned up for you. Do you need multiple objects? Well, use .vector, right? People are always preaching that, yeah? Just do it. If you need the object somewhere else, use .move, right? And don't access after you've moved from, right? So if you're only looking, well, there's weak pointer, right? Nobody uses it, so just use constref instead, if that's easier for you. I will have some comments on lifetime issues at the end of this talk. So identical expressions of binary operators, that seems to be a simple thing actually. So indicate typically a code defect in most cases. It seems like a copy-paste error and code duplication gone wrong. You had a rough day, right? At the end, just Control-C, Control-V. Give it a good polish at the end, and then you fail to update some case. And yeah, logical expressions can be tricky. So we do see in reality code like that, even more complicated. I mean, that still looks simple, right? But in reality, logical expressions can become quite complicated. And then you yourself, if you're not concentrated, sometimes you cannot see your own mistakes. And then it's nice to have some tooling, some analyzers, or even the compiler that freaks out and throws an issue or an error at you, saying, hey, go ahead and fix it. Function return value is also evergreen, can easily slip through. Well, again, enable compiler warnings and also then grep for return type to see if you are affected by that particular issue. The issue is the following. This actually really also only produces a warning, although in my opinion it should be an error. And if you're opposed to that, well, use an annotation. I'll talk about that later. So you have some critical task that needs processing, right? You do something, and then if you're successful, you return 1. And then you just forgot to return 0 in the other case. And well, undefined behavior, woohoo. And it will happily compile. And if you like hit the else branch, well, you just start executing the next instruction that comes after that, which is probably not what you wanted. So ensure appropriate return values on all paths, take compiler warnings seriously. And if you think, okay, hey, I have a function call, because you could also have some function call somewhere here, which just never returns, and then it would be okay-ish not to have a return statement, right? Well, then tell the compiler, tell your analysis tooling that you are hopefully employing, that the function is no return, right? It doesn't return, maybe it crashes after having like issued some warnings. That is typically like one use case of those of this no return keyword here or annotation. Also use no discard. So what I'm saying is communicate with your compiler. That really helps very much. So then identical branches, another copy and paste error similar to the logical expressions, right? We see that all the time where someone just copy paste and then, yeah, you call bar in the if branch and also in the else branch. Well, that indicates some logic error, and you should probably just simplify your code and just call bar without checking weird conditionals that are never taken into account. And this can really be seen in practice. So that either needs a fix or a simplification. Yeah, again, developers with concentration levels that already hit rock bottom, and then you come up with that. Destructors should not throw. Well, since C++11, destructors are implicitly no except, and if you still throw an exception in a destructor and it escapes the destructor's body, then std terminate will be called for you, and yeah, what happens then? Your program terminates in an implementation-defined, abrupt, and most of the time unclean manner, so you don't want to do that. Here's an example. So we can have a function foo. We set a terminate handler, which just prints to the command line, hey, that's really bad. Then we construct an object of type bad, whose destructor throws an exception. It doesn't bother at all to catch anything. And then when B goes out of scope here, boom, std terminate will be called. So it will then execute your terminate handler that you registered, and then all bets are off. So why is it an issue? Well, the reasoning behind that, as many of you, all of you should know, at least after having heard and read this slide. So imagine you are destroying a container, like say a vector, right? And then you need to call the destructors of each and every single object. And what happens if you fail halfway through? Well, you could abort, but then what would that mean? You would be left with an object in some half-dead, half-life state, and a whole bunch of other objects not being destructed at all. If you just ignore and continue, well, you already have kind of one outstanding exception. If you fail on yet another object's destruction, well, then again, std terminate it is. So both options are undesired, which is really why you shouldn't do it. And if you take some actions in your destructor that might throw, make sure you have a try-catch block and that no exception escapes the destructor in question, right? That is the recommendation here. Number 10, loops with at most one iteration. That still can be frequently seen in the wild. So frequently indicates a serious flaw in the program's logic, should be turned into a simple if. Here's an example, right? We have some loop, and then we execute that print statement, and then we have break and continue with our lives and whatever instructions follow. And well, that should be an if, right? I mean, nobody expects to use a loop for that purpose. At worst, and that is probably true in reality, that was not the initial intent of the author, and yeah, now you have a more serious problem because that really seems to be a hefty logic error. Okay, don't believe me? Well, I see bugs. I now show you some examples that can be observed in the wild. So let me try to convince you further. So Notepad++. Well, is point valid? Well, we have a point comprising x and y value. Is x valid? And yeah, let's better check again. Maybe it changed in the meantime. But no, that is probably not what was intended. So that should be, is point y valid? And yeah, that is, you should do something about it. Let's have a look at another example where we have a while loop. We seem to compare some stuff, right? Yeah, pointers and such, buffers, manual memory management. Anyhow, okay, so let's go with that then. While loop, we decrement the size counter variable and check if it's greater or equal than 0. And if so, we execute what's in that loop. However, well, size is of type std size t, which is unsigned. So it can never be smaller than 0. And the great thing, at least, is, hey, overflow is well defined for unsigned types. So it would just go forever and ever and ever until you probably dereference some memory that is not yours here using these pointers. And then you're dead. Not good. Okay. What else do we have? Yeah, you can never be sure. I mean, I told you stuff about null checks, right? If you have a pointer, so let's check if the pointer is really not null before we continue. And then we again check if it's really not null, but just with a slightly different spelling, but essentially it's the same check. So yeah, better safe than sorry. But I guess what was meant here was adding a star here. So we wanted probably to dereference that pointer to kind of get the empty string case handled. Again, manual string management, string buffers, don't do it. You can only fail if you try to do it. Null pointer checks. Let's check if we have a null pointer. And if we do have a null pointer, let's access stuff and try to get the most of it. That's not good, right? I mean, and the developer kind of was aware of that. So there was a check written, but by accident, no concentration level anymore. Yeah, let's check. Let's do it the other way around, that you exactly hit the bad case. Again, compilers and static analyzers can help you with that, right? They can catch your weak moments. That is really helpful. More stuff. MD5, buffers, manual management of buffers. So 64 bytes, uint1, that is probably a byte or something, right? So 64 bytes buffer. Well, we do some security critical sensitive stuff, and at the end we want to zero it out, right? That's good style, good practice in cryptography. First of all, you shouldn't use memset because the optimizer might be throwing that away because, hey, nobody is using that buffer, why should I zero it out? I mean, if it's not used anyhow after that zeroing out, I just also throw away that zeroing out. So yes, there are alternatives in any sane cryptographic library for a secure zero out. And then on the other hand, what happens here? Well, I dereference that buffer pointer. And then, so that is an individual element of that buffer. And then I take its size, which is probably only 1 byte. So I just write 1 byte of 0 into that buffer, that's complete garbage, right? I mean, that is not good. More stuff on strings. Well, skip blanks, so remove all the white space before and after some string, right, if any. And I mean, there are examples like this where it's harder to see. But then again here, a star is missing. Like here we would need to reference, and what else? Here also we would need to reference to make it somehow correct. But you can never be sure, right, because you're fiddling around with string buffers on your own. It's not a good idea. So that's also buggy. It goes on forever. Really, for days, I can show you the best parts, and it's really crazy. It's really fun, yeah. So now what? let's recap for the first time here now. So what can we do? We don't even seem to get the easy parts right. In my opinion, we shouldn't even be discussing most of this. Use string, use vector, use unique pointers and all that good stuff. So modern C++ can mitigate most of these problems. And tooling and analyzers, those can help to catch your weak moments where you are really just not concentrated anymore and you write some stuff that you shouldn't be writing. So you think you wrote your code does one thing and your code does something completely else. Those cases can be caught by tooling. So open questions, I mean, still we have those findings, right? Have we failed at teaching C++? And sometimes, I believe, if you look at some university courses, it seems older professors still, it's like C with classes, and maybe let's teach it that way, because people learn how memory works if you do that. That's quite expensive in the long run. Open question, I'm happy to discuss that after this talk. Is it simply all legacy code? I don't know. I don't have an answer. Are we just using the wrong defaults? Here I would say personally yes. So like with the uninitialized variable stuff, so just make everything 0 initially and then at least you wouldn't have undefined behavior. That's just one example, but I mean, sometimes I feel really we are using wrong defaults. And you should probably have it the other way around. And if you really want to be blazingly fast, even at the cost of safety, well, then flip some compiler switch and then the compiler just shuts off any checking at runtime. Well, language adoption is slow. That is maybe one argument. More than C++, we teach it, we preach it, and we see it at conferences, but until it really happens in reality, in your day-to-day code bases, that is notoriously slow. That's a slow process, right? So even if you all now jump on Rust, I mean, that wouldn't help our problems here immediately. I mean, just to pick up on Titus's comment in the morning. So language adoption is slow. So, and unfortunately, they're also statically hard to find bugs. Let me walk you through. So there are limits. Static analysis is impossible for arbitrary code. So you can always write a piece of code that completely defeats static analysis. That's quite sad, but yeah. That's partially due to Rice's theorem, which I talked about earlier. And whole program analysis is also prohibitively expensive. If you think about that symbolic execution, analyzing program path by path, if you have your 100 million lines project, well, good luck with that. Lifetime of universe would be shorter than the amount of time that a symbolic execution would need to analyze the program. All right, what can we do about that? Well, at least we can help static analysis, so we can use the appropriate types and libraries. Hey, here are your friends, right? Stud variant. On rare cases, you need unions. I would say at almost none. Yeah. I mean, okay, there are fishy driver computation, if you implement drivers and the good stuff, well, okay. But here, if you really need it, encapsulate your low-level and funny code and make sure you throw everything you've got other than static program analysis at it, namely dynamic analysis for the most parts in order to like iron out all the bugs if possible. So compilers and analyzers love local reasoning. So should you if you write some code and the reviewer of your code, hopefully you do have a reviewer, so some other guy looking at your code before it goes into your main branches. You should implement a change if that's not the case. They will be quite upset if, in order to understand your function implementation, if they all of a sudden need to walk through the whole code base because you're calling a gazillion different functions at different places. You should craft implementations that you can really reason in a local manner about them. And not only your reviewers love that kind of local reasoning, but also your static program analyzers and also the compiler. I showed you the example with the magic initialization function, which didn't do anything. It just took an integer as a reference. And then the compiler already throws its hands in the air and says, okay, I don't know any better, so I'll just run away and don't do anything and don't issue a warning. Well, you can also help those tools and the compiler by expressing intent, use annotations. Those are taken into account. No return to silence, like missing return of a function. Maybe unused if you are annoyed by compiler warnings that say, hey, that variable is unused, and maybe you have a good reason for that, and then just make it explicit. Right? So one thing that has bitten me a few times already, lifetime. All good. You stood string, you stood vector. Careful with using std string view or std span or really any reference for that matter, because you should make sure that the object you are referring to still outlives the lifetime of the reference, right? And I found this note here on cppreference.com for basic string view. It's the programmer's responsibility, and again, famous last words, to ensure that std string view does not outlive the pointed to character array. And there are some easy cases here. You have a string s, and then you have a string to it, and all is good, right? I mean, easy to see, right? Okay. Well, you also have another good case for string view that is just that exists as a static, as a constant global variable. That will be just a constant global character array in your compiled binary. That is also good. That is not so good, although it would work. in the sense that it would compile, and then you have an issue. So you can have a string s, right, and you just add some more bytes, and this then creates, this expression creates a temporary string to which you take a reference, which is a bad reference, right, because at the end of the expression, at the end of the semicolon, the temporary string will go away, and then you have your bad reference pointing to nirvana. So that is not good. All I guess I want to say is there are really difficult cases which are hard to see. One more issue. Yeah, again, I program analyzers and I use C and C++, and I also use LLVM and Clang. And in LLVM, we have that dense map implementation, which is a very fast hash map implementation, which you can use to hash and to cache stuff potentially. And what you can write the following, right? So you can say, hey, map, try in place. So give it some key and try to in place. And then you get the iterator and a bool, which tells you inserted yes or no. If the insertion took place, well, that means there is no such thing with that value just yet. So maybe I do perform now an expensive computation, and I write it to the iterator I get, basically, and to correctly initialize it. If the insertion did not take place, well, then there has been already some value associated with that key, and I can just use it directly and maybe print it to the output stream, what have you. The problem is, that's a real example, so that is a bug that I created. I also do make mistakes. So I had some more complex code in between. I was under some conditions, I was also inserting even more stuff into that map. And now I have to tell you, well, that map implementation, it doesn't use node-based allocation, but instead it allocates whole chunks, puts in key value pairs. And if that chunk is no longer sufficient because you add more, then it allocates more and copies your stuff to yet another place, right? So it reallocates, and that was kind of disaster because here that iterator was invalid at that point. I was using it, but only for some examples, because in some test cases, well, I just didn't put too much stuff into it, so it would be perfectly fine with the originally allocated chunk of memory. In other cases, it was not. And this is one of those things really hard to detect statically. So what I did use instead is try address sanitizer, and luckily it almost immediately pointed me to the issue. So what would you do is you would just flip that switch, say, hey, fsanitize address, and maybe add some debugging symbols for better readability of that trace that you get. Then you execute your bad code, and then it will throw kind of a trace at you, and that can be used then to detect that issue. And then with that message, I immediately knew what was happening, and I could fix it. Yet another example which is really hard to detect and to debug in reality, in real-world systems, are race conditions, right? I mean, that's a simple example. We have a global variable which is 0 initialized. Luckily, at least the globals are 0 initialized because it doesn't come with an additional cost. It can be done at compile time. And then we start one thread which writes the integer literal 13 to that global variable, and then the main thread continues and writes 42. Well, the actual value of that thing you are returning depends now on whoever comes first, comes last, that way. So you have a race condition. That's really difficult to detect. First of all, to be aware that your program suffers from a race condition, and it's even harder to debug. Again, static analysis, there are theoretical concepts that would be theoretically able to detect it. It's hugely complicated. It's even more complicated to implement that stuff. And it does not scale. It's just too expensive if you try to have that really fancy, researchy technique, prototype implementation running on a code base with 50 million lines of code or more. Then, I mean, all bets are off. It just won't finish. Cannot be done to this date. let me know if you know that someone else succeeded in that matter or on that matter. So instead, you can also use another sanitizer, which is the threat sanitizer. So you can compile your program again, run it, and it will tell you, hey, I found that data race here. And it will tell you like whatever the threats did that led to the race condition. So that is also quite handy to detect and fix those race conditions. So dynamic analysis mitigates blind spots. So whenever static analysis doesn't know any better, use sanitizer builds maybe. So in addition to your release and your debug build, nowadays you should have sanitization builds, right? And then have your sanitization builds and run them through your test suite. And you should have a test suite. Otherwise, you have some homework to do, right? Some people say, hey, we should run that in production, right? I say careful with running sanitizer builds in production because those heavily instrument your code and you can potentially open up your program to like malicious attacks. It can make them easier to exploit. So before you say, hey, it's a good idea, let's run that in production and see what we actually, what we get, think about it twice. It can be potentially dangerous. Run your code and test suite through Valgrind. So I know many projects whose test suite have a switch. You can just add another flag when running the tests, and it says then, hey, run every single test through the Valgrind, which is mostly a memory error detector, dynamic analysis, and it will find a lot of stuff. That is quite surprising. So, what can we do today? Well, it seems we need to improve on teaching C++, and I'm not necessarily talking about the teaching that this community does, but it has to start much earlier at the universities. I guess that is one aspect where we currently fail. Use C++ like it's 2024. Again, on my top 10 list, like half of the issues could be mitigated by just not using C-style strings and all that crappy stuff. So don't do it. Right? Employ static analysis to catch bloopers, right? Having the same expression on both sides of the binary operator. That is really just unconcentrated developers. Checking for not null instead of null. Like I showed you that example. Those things can be caught by compilers at best. Otherwise, you can throw compiler-based tools like ClankTidy at it, and then you have your dedicated static program analyzers. Choose your favorite one. It will find a lot of amazing stuff that you didn't even think of. Compilers and analyzers love local reasoning, so should you. So your reviewers will be thankful, and the tooling will also have a better time. The static analyzers will have a much better time. We'll be able to find much more. And use dynamic analysis to mitigate blind spots where static analysis just can't help you because of the limitations I talked you through. Well, that concludes my talk. I am now happy to take any questions on any of that matter. So thanks very much.
Hello. Is your company or anyone you know looking to large language models as another tool to catch like this kind of bugs?
Yes. I can't give you too many details, but it seems that trend of AI has reached like also the static analyzer companies these days, and people are working on it. The outcome, I am not a fan of that AI stuff, so I am with Titus, who made a strong claim, strong statement about that, right? And I share that view on things. So you can certainly use it with some success. There are several research papers that show you can find some interesting stuff. You can find issues and bugs using AI and LLMs, but I'm not sure.
Hi, long-time user of your products. Great. And really important, I think. question, just because I'm curious. At the beginning, you mentioned that Sonar has like a dozen languages or so in their portfolio, and that you have like 6,000 rules. I guess those are across all the languages. I guess that C++ makes up the majority of those rules because the language is so complex.
Like
is that true?
660-ish rules for C++.
Okay. Okay, maybe that's because it's really hard to come up with rules that work in C++ as well. But I think my personal experience is that there's a lot of things that can go wrong in C++ that can go easily wrong in other languages. But on the other hand, the rules there are often easier to implement. So, yeah, I guess it wasn't really that much of a question then. Sorry.
All is good.
I have a question from online.
Sure.
So you mentioned that static analyzers have a trade-off between false positive and false negative. I would like to know the techniques. The techniques used under the hood by static analyzers to get that trade-off. Will reporting false positives get better over time?
It helps very much if you report false positives. We have dedicated channels where users can report such false positives, and we try our best to mitigate that. How is the trade-off done? Well, it's our engineers who write the implementations that check the rules, and they are making the decisions within the implementation. So it's not, unfortunately, for the most part, you cannot have a magic parameter between 0 and 1 where you can like granularly say, okay, hey, I want only, this is my threshold and I want only so many false positives or false negatives. So that doesn't work. But the false positives that we get reported, we try to fix. Yeah.
Thanks for the talk. Could you maybe say a little bit about how SonarCube compares to other static analyzers like JetBrains, Codano, or something like that?
No, I can't actually. And that's not on us. Some of those analyzers have interesting licenses which prevent doing any kind of comparison. It's against the law, and then they would have a huge lawsuit if that comes out. So yeah, that's my answer. Sometimes you have some research papers which like try to showcase and do some comparisons between different static analysis tools. Can be interesting, can be helpful. Yeah, but that's the best I can do and provide you with as an answer.
Thank you.
Hi, thanks for the talk. With you working with multiple companies, do you see any correlation between the amount of tests people implement and the amount of errors? Like, is there any correlation with the amount of tests and the amount of errors that you get from them?
I didn't get the second part. Is there a correlation between the amount of tests and what was this?
And the errors.
The errors.
Yeah.
Well, no, I don't have hard numbers on that one. I can tell you how we do it at Sonar. For every piece of code, we do have a whole bunch of tests that like try to test the important cases, right? You will never be able to like have everything covered, but we try to have like a high test coverage. Again, I can't like correlate this. I don't have numbers for that.
Okay.
But I could compute those maybe.
So would you still advocate for test-driven development, kind of, or writing?
That's a good starting point. Yes, test-driven development is always a good starting point to make yourself aware of, hey, what actually needs to be done, right? And you catch lots of things with tests. And also, you need tests if you want to use dynamic analysis, right? If you have your sanitizer builds and other dynamic program analyzers, you need something that suitably reflects reality to have meaningful results using dynamic analysis techniques. So it's you only win if you have tests.
Okay, thank you.
All right, thanks very much.